Assalamu alaikum students. In today's lecture we are going to learn mathematical induction and strong induction, and this lecture covers section 5.1 and 5.2 of the textbook. So let's start with 5.1, which is mathematical induction, and the summary of the section is as follows: mathematical induction, examples of proofs by mathematical induction. Then there are a few guidelines to use mathematical inductions correctly. So what is mathematical induction? Mathematical induction is like climbing an infinite ladder. So what steps we need to make sure to climb the ladder? First step is that we can reach the first rung of the ladder. So we must reach first rung of the ladder in order to climb the ladder up. And the second step, which makes sure that we can climb the ladder up till infinity, is that we can reach a particular rung, which is kth rung of the ladder. If we can reach that particular rung of the ladder, then we can reach k plus 1 rung of the ladder as well, right? So if we make sure these two steps, then this implies we can climb every rung of the ladder, or we can climb an infinite ladder. So here is mathematical form of principle of mathematical induction. The principle of mathematical induction states that in order to prove that Pn is true for all positive integers n, we have to follow these two steps. First step, basis step. In this step we show that P1 is true, that the statement is true for n is equal to 1, and second step is called inductive step. That is, if pk is true, then pk plus 1 is true. That is, pk plus 1, we can prove the statement is true for n is equal to k plus 1 whenever it is true for n is equal to k. So instead of proving this Pn to be true for every value of n, for infinite value of n, these two steps concludes that proving these two steps concludes that Pn is true for all positive integers n. And this is how we can compare the principle of mathematical induction and climbing the ladder, because climbing an infinite ladder, the first step of or the basic step of climbing an infinite ladder is that we can reach rung 1, and the inductive step in this case is assume that we can reach rung k, and this implies we can reach rung k plus 1. So hence, if we can prove these two steps, that is P1 is true and Pk is true, implies Pk plus 1 is true, then we can reach every rung on the ladder, that is Pn is true. So there are a few important points to be remembered while using mathematical induction. Mathematical induction can be expressed as a rule of inference, P1, and for all k, Pk implies Pk plus 1 implies for all n Pn, where the domain in the set of is a set of positive integers. And mathematical induction, this is how it works. Consider an infinite sequence of dominoes labeled 1, 2, 3, and so on. That is positive integers, and where each domino is standing. This is very important, that initially each domino is standing. So let Pn be the proposition that the nth domino is knocked over. A domino is a rectangular piece. Note that the domino is a rectangular piece, that is 1 square by 2 squares. So knowing that the first domino is knocked down, that is P1 is true. Now we also know that whenever kth domino is knocked over, it knocks over the k plus first domino. So Pk implies Pk plus 1 is true for all the integers k, hence all the dominoes are knocked over, that is Pn is true for all positive integers. So let's solve the first example using principle of mathematical induction, and the question here is show that sigma I varies from 1 to n is equal to n into n plus 1 divided by 2, or we can rephrase this problem as that the sum of first n positive integers is n into n plus 1 divided by 2. So let's solve this by using mathematical induction. Basis step is P1 is true because 1 into 1 plus 1 divided by 2 is equal to 1. 1 is equal to 1, that means P1 is true. Inductive step, assume that Pk is true. Pk true means that we have to suppose that sigma I raised to 1 to k, that is n is replacement of k, of I is equal to k into k plus 1 divided by 2. Now we have to prove that this if pk is true, pk plus 1 is also true. Now what is pk plus 1? Actually we have to prove that sigma I raised to 1 to k plus 1 I is equal to k plus 1 into k plus 1 plus 1 divided by 2. So let's see how does it work. So under the assumption, what we have to prove, let's start with the statement of left sides of the statement, that is 1 plus 2 plus k plus 1, right? So these first k integers, sum of first k integers can be written as k into k plus 1 divided by 2 according to our assumption that pk is true, plus k plus 1 as it is. Now let's have LCM, which is 2. So we have k into k plus 1, 2 into k plus 1, and that can be written as k plus 1, taking k plus 1 common, and from both the terms we have k plus 1 outside and inside we have k plus 2, and k plus 2 can be written as k plus 1 plus 1. So this implies if pk is true, because we used the fact that pk is true, if pk is true then pk plus 1 is also true, and this implies p. Alright, now let's do another example. In this question, we need to prove that 1 plus 2 plus 2 square plus so on to n is equal to 2 to the power n plus 1 minus 1 for all non-negative integers n. For all non-negative integers n means that the lowest integer for this result would be 0, which satisfies the this equation. So our basis step will start from 0, p0. In the basis step we have to prove that p0 is true. So let's assume pn first. So let's assume pn is the statement for all non-negative integers n. Now the basis step p0 is true since when n is 0, 2 to the power 0, here we have only 2 to the power 0, which is 1, and right side of this relation is equal to 2 to the power 1 minus 1. So this is again 1, so this is true. Now inductive step, in this step we are going to assume that pk is true. So this is just an assumption, and you have to mention that let's assume that pk is true for an arbitrary non-negative integer k, that is this result is true, this equation is true for any non-negative integer k. Now with this assumption we have to prove that pk plus 1 is true. That is, if this is true, then we have to prove that this statement is true, right? This statement is true. Now for this, consider left hand side of the statement. This is what we have to prove, so keep it in mind, and this is what we have to prove using the fact that pk is true, that is this statement is true, right? So left hand side of this pk plus 1, let's consider this, which is equal to, let's split it into two parts. First part is pk, is the left side of pk, and we are left with one term, which is 2k plus 1. Now this is equal to, now this can be written as 2k plus 1 because we have assumed that pk is true. Since pk is true, so this side is equal to 2k plus 1 minus 1. So this is replaced by 2k plus 1 minus 1 plus 2k plus 1 as it is. Now this can be written as 2 into 2k plus 1 minus 1, right? How did we do that? 2k plus 1 one times. Now here is another 2k plus 1, which makes it 2 times. So we have 2 times 2k plus 1, and we are left with minus 1, so minus 1 as it is, which is equal to 2 into 2k plus 1 is 2 times 2 to the power k plus 1 plus 1. So this is equal to 2k plus 2 minus 1. So this is equal to right hand side of pk plus 1. So that this implies pk plus 1 is true. Now pk plus 1 is true whenever pk is true, means Pn is true for all non-negative integers n. So don't forget to write this conclusion, right? So it has basically 3 steps. First of all, rather 4 steps. First of all, we need to figure out what is Pn, then basis step, then inductive step, and then finally the conclusion. Okay, another example. Conjecture and prove correct formula for the sum of the first positive odd integers. Then prove your conjecture. So first we need to guess what is what could be the sum of first positive odd integers, first n positive odd integers, and then we'll prove the result by using method of mathematical induction. So first of all, if we have one odd integer, we have 1 is equal to 1, and we have two odd integers, then 1 plus 3 is 4. Now one odd integer sum is 1. Two odd integers sum is 4. Now first three odd integers sum is 9. First 4 odd integers sum is 16. So first 5 odd integers sum is 25. So we have a pattern here. If we add one integer, we have 1. We add two integers, we have 2 to the power 2, that is 2 square. Now if we have three odd integers, then their sum is 3 square. If we add 4 odd integers, then the sum is 4 square. If we add 5 odd integers, the sum is 5 square. So we can follow the pattern and conclude that the sum of first n odd integers is equal to n square. Now the question here is, what would be the nth odd integer? Now see, we have two odd integers and the second integer is 3, right? And we have three odd integers, the third integer is 5. So what would be the nth odd integer? You can figure it out by using arithmetic sequence rule. That is, nth term of the arithmetic sequence with first term 1 and common difference 1 is 2n minus 1. So we have 1 plus 3 plus 5 plus so on 2n minus 1 is equal to n square. That is, sum of first n odd integers is equal to n square. So let's prove this by using mathematical induction. So in this case, our Pn is 1 plus 3 plus 5 up till 2n minus 1 is equal to n square. And in order to prove P1 is true, we just consider the statement for n is equal to 1. So left hand side it becomes 1 because number of odd integers in this case is 1, and right hand side is 1 square. So 1 square is equal to 1. P1 is true. And the next step, we assume that Pk is true, and we'll prove that Pk plus 1 is true whenever Pk is true for every positive integer k. So assume Pk is true means that this statement is true. Now assuming that Pk is true, we'll prove that the sum of first k plus 1 odd integers is k plus 1 whole square. Now what does the sum of first k plus 1 odd integers look like? So it looks like this. This is the sum of first k odd integers. Now first adding k plus first odd integer, which is 2k plus 1, and this is equal to, it can be written, it can be split into two parts. The first part is the sum of k odd integers and plus the k plus first odd integers. Now since sum of first k odd integers is assumed to be k square, so we just plug in the value of this, which is equal to k square plus 2k plus 1, which is k square plus 2k plus 1, which is equal to k plus 1 whole square. So we have shown that Pk plus 1 is true whenever Pk is true, and this implies that Pn is true for all the positive integers n. Next example, use mathematical induction to prove that 2 to the power n is less than n factorial for every integer n greater or equal to 4. So in this case, our basis step will be P4 because we are starting from n is equal to 4 for every integer greater or equal to 4. So the smallest integer in in its domain is 4. So we'll start with 4. So first of all, figure out what is Pn. Pn in this case is 2n less than n factorial for n greater or equal to 4. Don't forget to write this, n greater or equal to 4. So basis step. We'll start with P4 as I have already mentioned. P4 is true because 2 to the power 4 is equal to 16 and 4 factorial is 24 and 16 is less than 24. So P4 is true. Now inductive step. In this step, we'll assume that pk is true, that is 2 to the power k is less than k factorial for any arbitrary integer k greater or equal to 4, and we'll prove that pk plus 1 is true whenever pk is true. So just consider pk left hand side of pk plus 1, that is 2 to the power k plus 1. 2 to the power k plus 1 can be written as 2 into 2 to the power k, and this is less or equal to 2 into k factorial by the hypothesis of induction. Now k factorial is as it is, and we just replaced by 2 by k plus 1. Now since k is greater or equal to 4, since k is greater or equal to 4, so keep this fact in mind, k is greater or equal to 4, so least value of k can be 4. So we can have k plus 1 as 5, but 2 is less than 5. So 2 is always less than k plus 1. So this inequality is not altered by substituting this. So 2 is less than k plus 1. So we replaced 2 by k plus 1 and k plus 1 multiplied by k factorial, which is equal to k plus 1 factorial. So in such cases, you just need to keep in mind that what we are going to prove, right? So conclusion must be k plus 1 factorial. So our target is to manipulate like this so that we can have k plus 1 factorial on the right hand side. So this is how we prove that pk plus 1 is true whenever pk is true. So therefore 2 to the power n is less than n factorial is true, that is pn is true for every integer n greater or equal to 4. Okay, next example, use mathematical induction to show that if S is a finite set with n elements, where n is a non-negative integer, so n can be 0, we can have an empty set as well, then S has 2 to the power n subsets. So since this statement is for non-negative integers, so we'll start with P0. So let's write Pn first. Pn be the proposition that a set with an element has 2 to the power n subsets. So basis step is P0. P0 is true because the empty set has only itself as a subset, and that is, it has only one subset, and 2 to the power 0 is equal to 1. Inductive step. Assume that pk is true, that is pk is true, that is the set with the k elements has 2 to the power k subsets. And now we will prove that pk plus 1 is true whenever pk is true. So let T be the set with k plus 1 elements, and T is equal to S union A, where A belongs to T and S is equal to T minus A, right? So we assumed that we have a set T which is S union A, a singleton set A, right? Now A belongs to T and S is equal to T minus A. For each subset X of S, there are exactly 2 subsets. So S is this. Now there are exactly 2 subsets of T, X and X union A. By the inductive hypothesis, S has 2 to the power k subsets. Since there are 2 subsets of T for such subset of S, Thus, the number of subsets of T is 2 times 2 to the power k, and which is equal to 2 to the power k plus 1. So, this proves that pk plus 1 is true whenever pk is true. And this implies Pn is true. Now there is an important remark that when we show that the inductive step is true, we don't show that pk1 plus 1 is true. Instead, we show that the conditional statement is true. That is, whenever pk is true, pk plus 1 is true. And we always end up the proof with the conclusion. Don't forget to write this. Mathematical induction is very powerful technique because we show just two statements, but this can imply infinite number of cases to be correct. Okay, this is the template of a proof by mathematical induction. These are the steps to be followed. Express the statement that is to be proved in the form for all n greater or equal to b, Pn. So, as we learned in previous examples, that first step is to figure out what is Pn, and secondly, basis step, that is Pb is true, and then the inductive step in which we assume that pk is true for k greater or equal to b, and then we prove that pk plus 1 is true whenever pk is true. Okay, so you have to make the argument that pk is true in order to prove the fact pk plus 1 is true. And when pk plus 1 is true, whenever pk is true is proved, then this identify the conclusion that is Pn is true for all n greater or equal to b. Now next section, strong induction and well ordering. So this consists of the following steps. Strong induction. Strong induction to prove that Pn is true for all positive integers n, where Pn is a propositional function. Complete two steps are followed. First step is basis step. Verify that the proposition P1 is true. Right? This is similar to the weak induction we have already done. Inductive step is different from the weak induction. Show the conditional statement P1 and P2 and up till Pk all are true implies Pk plus 1 is true, right? So what is the difference between in this case? In this case, we have to figure out that when we prove that pk plus 1 true, before proving this, we use that p1, p2, p3, p4 up till pk all are true. So we make sure that we are able to reach every rung on the ladder before the k plus first rung, right? So this is the difference. In the weak induction, we just make sure that we are able to reach step 1, and then we assume that we can reach step k, and we use this assumption to prove that we can reach step k plus 1. But in this case, we make sure that we can reach every step before k plus 1, and we use all these results to prove that we can reach step k plus 1. So this is the generalized version of mathematical induction. This is called strong induction. So let's illustrate the process with the examples. So first example, show that if n is an integer greater than 1, then n can be written as the product of primes. So first step is same. We just need to write Pn, and in this case Pn be the proposition that n can be written as the product of primes. and where n is greater than 1. So basis step, we'll start with P2 because n is greater than 1. So we'll start from n is equal to 2. So P2 is true because 2 is prime number itself. So by default it can be written as product of primes. Now inductive step. Now this is a little tricky. Inductive hypothesis will assume that Pj is true for all the integers j lies between 2 and k. So using the infinite ladder, I told you that you have to reach every step before k plus 1. So we are assuming here that Pj is true for every j lies between 2 and k, including 2 and k. That is, j can be written as the product of prime where j is a positive integer at least 2 and not exceeding k, right? Now to complete the inductive step, we have to prove that pk plus 1 is true under this assumption. Okay, now there are two cases. First case, if k plus 1 is prime. If k plus 1 is prime, then there is nothing to prove. Like in basis step, since 2 was prime, there was nothing to prove. So if k plus 1 is prime, so we immediately see that pk plus 1 is true. And otherwise, if k plus 1 is composite, and then it can be written as the product of two positive integers, any integers a and b, where a, b both are greater or equal to 2 and less than k plus 1. Okay, because both a and b are integers at least 2 and not exceeding k. So we can use this inductive assumption. A and b both can be written as product of primes. Now since k plus 1 is equal to a multiplied by b, and a and b both lies between 2 and k, so both can be written as product of primes. So in this way k plus 1 can be written as product of primes, and this means pk plus 1 is true whenever p2, p3 up till pk are true. So this leads us to the conclusion that any integer can be written as product of primes. Next example. Prove that every amount of postage of 12 cents or more can be formed using just 4 cents and 5 cents stamp. Okay, read it again. Prove that every amount of postage of 12 cents or more. Okay, we are not talking about the postage of the amount less than 12 cents. We are talking about the postage of amount 12 cents or more. So every amount of postage of 12 cents or more can be formed using just 4 cent and 5 cent stamps, right? So let's see how to prove this. So we'll first try this mathematical induction to prove this, and for this basis step, postage of 12 cent can be formed using 3 4 cent stamps, which is quite obvious. 12 cent stamp can be formed by 3 4 cent stamps, so 3 multiplied by 4, and this is true. So inductive step, assume that pk is true, and we are using weak mathematical. This is not strong mathematical induction. If you are wondering what is happening, so this is not strong mathematical induction. Assume pk is true, that is postage of k cents can be formed using 4 cent and 5 cent stamps. Now to complete the inductive step, assume that pk is true, then pk plus 1 is also true. So we need to prove that pk plus 1 is true. Our assumption is pk is true. That is, we have to prove that every we have to prove that if every every stamp of k cents or every postage stamp of k cents can be formed by 4-cent and 5-cent stamps, then k plus 1 can also be formed by 4-cent and 5-cent stamps. So this is the target. We have to prove that. Now there are again two cases when at least one 4-cent stamp has been used and when no 4-cent stamp have been used. Okay. So let's consider the first case. Suppose that at least one 4-cent stamp was used to form postage of k cents. Then we can replace this stamp by 5 cent. When we add 1, okay, we are assuming that at least one 4-cent stamp was used to form postage of k cents. That means rest of the stamps are 5-cent stamps. At least one means we are using at least one. It may be the number of 4-cent stamp may be 2, 3, or greater than 1, but at least one stamp is used. 4-cent stamp is used. So when we are trying to form k plus postage stamp of k plus 1 cents, then we just add 1 into 4-cent stamp, and this will become 5-cent stamp. Rest is already in the required form, so 4-cent stamp becomes 5-cent stamp, and our k plus 1 cent stamp can be written as 4 and 5-cent stamps. So the next case, if no 4-cent stamp were used, so we can form postage of k cents only 5-cent stamps, right? Now since k is greater or equal to 12, so if the stamp is made by using only 5-cent stamps, then the least number or the least amount we'll pay for the stamp will be 15 cents. Okay, I hope you get it. If there is no 4-cent stamp is used, that is all the stamps used to make 15 to make k plus k stamps is a 5-cent stamp, right? So it means k is multiple of 5, in other words, right? K can be 5, k can be 10, k can be 15, k can be 20, and so on. But our condition is on k is greater or equal to 12. So the least value of k, which is multiple of 5, can be 15, right? So we needed at least 3 5-cent stamps to form postage of k cents. So it can be 15, least value will be 15. So it can be 15, it can be 20. So 15 is there in the amount, whatever k is. Okay. So when we add 1, this 15 will become 16, right? So 16 plus rest of the multiple of 5 stamps. So this 16 can be written as 4 times 4, and this can be represented by 4-cent stamps. So again, we are able to find a representation in 4-cent and 5-cent stamps of k plus 1 cents. So this completes the inductive step, and finally the conclusion. Don't forget that. This concludes that our Pn is true for n greater or equal to 12. That is, postage of 12 cent can be formed using 4-cent and 5-cent stamps. Postage of 12 cent or more can be formed using 4-cent and 5-cent stamps. Next example. Another way to solve this example. So I'll leave it for your exercise. I'll share the slides. You can see the proof and try it yourself and let me know what are your findings. Next example. Consider a game in which 2 players take turns removing any positive number of matches they want from one of 2 piles of matches. The player who removes the last match wins the game. Show that if the two piles contain the same number of matches, initially the second player can always guarantee a win. So we are going to play a game, okay? And we have two players, right? And both have same number of matches with them. Matches, bole to matches, okay? So consider a game in which two players take turns removing any positive number of matches they want from one of two piles of matches. So both have a pile of matches, and the player who removes the last match wins the game. So the game here is one player has one pile of matches, two other player has another player of pile of matches, and both the piles contain equal number of matches, and they remove turn by turn equal number of matches from the piles. Okay, I hope you get the question. Now let's try to solve it. Now target here is we have to show that if the two piles contain the same number of matches initially, the second player can always guarantee a win. Initially both the piles contain same number of matches and the players remove same number of matches as well. Okay, so this is the condition. Now the solution: let n be the number of matches in each pile. We'll use strong induction to prove Pn, the statement that the second player can win when there are initially n matches in each pile. Basic step: when n is equal to 1, the first player has only one choice. He will remove one match and he will be left with no match at all. But second player still have his match with him, so he will remove his and he will win the game, because winning strategy here is the player who removes the last match wins the game. Okay, so the second will remove the last match and he will win the game. So P1 is true in this case. Now inductive step. The inductive hypothesis is the statement that Pj is true. Now we are going to assume that Pj is true for all j when j lies between 1 and k. That is the assumption that the second player can always win whenever there are j matches, where j lies between 1 and k. In each of two piles at the start of the game, we need to show that pk plus 1 is true. That is, the second player can win when there are initially k plus 1 matches in each pile. So under this assumption that pj is true for j is equal to 1 to k, suppose that there are k plus 1 matches in each of the two piles at the start of the game, and suppose that the first player removes r matches in the first turn and leaving k plus 1 minus r matches in the pile. So by removing the same number of matches from the other pile, the second player creates the situation where there are two piles, each with k plus 1 minus r matches. Now since k plus 1 minus r lies between 1 and k, so using our assumption Pj is true, we can now use the inductive hypothesis to conclude that second player can always win. So this completes the proof. That is Pk plus 1 is true whenever Pk is true, and this implies that Pn is true. Next example.